So we are back to start talking about section 10C, gases in the mole. And gases were very important. The study of gases was very important in developing the concept of the mole. So we're going to take a look at that idea today, starting with section 1011, the law of combining volumes, gases in reactions. So Gay-Lussac, he studied gases, and he actually came up with this law of combining gases. And he observed that when you combined 1 mole of hydrogen gas plus 1 mole of chlorine gas, and actually he didn't know anything about the mole, okay, but this was later discovered, you get 2 moles of hydrogen chloride. We know this from our equation. Okay, what he observed was that when you combine 1 liter of hydrogen gas and 1 liter of chlorine gas, you get 2 liters of hydrogen chloride. It was later discovered that we could use the idea of the mole and that these were also molecules combining, but he did not know that at the time. We also know today that if we combine 2 moles of hydrogen gas and 1 mole of oxygen gas, we get 2 moles of water. Likewise, what Gay-Lussac observed was that 2 liters of hydrogen and 1 liter of oxygen gas combines to form 2 liters of water. Gas, that is. And we also know from our equations today that 2 moles of nitrogen gas plus 3 moles of hydrogen gas gives 2 moles of ammonia gas. And what was observed by Gay-Lussac was that 1 liter of nitrogen and 3 liters of hydrogen gave 2 liters of ammonia. So what we see here is that the mole ratio equals the volume ratio. And that is also what you observed in the video of water electrolysis. What you were observing was this equation here backwards. So they were taking the water and splitting it into hydrogen and oxygen. And what is observed is that twice as much hydrogen is produced as oxygen. And you might think that there should be more oxygen than hydrogen because oxygen has more mass, and so therefore perhaps it should take up more space, but that is not the case, and we're going to talk about that, why that is true as well. So this is what was observed. And because this is what is observed, the law of combining volumes was developed, and it states, under equivalent conditions, the volumes of reacting gases and their gaseous products are expressed in ratios of small whole numbers. So this led to section 1012, which is the molar volume of gas. I'll give you a few seconds. I forgot to give you a few seconds to pause for the previous, but I bet you probably did. Okay, so section 1012, the molar volume of gas. And surprise, surprise, Avogadro worked on this, and he developed Avogadro's law, which states that the volume of a gas maintained at a constant temperature and pressure is directly proportional to the number of moles of the gas. So he developed this idea of moles. He said, well, these volumes, we see this happening with the volumes. We can relate it to the number of molecules to the number of moles. And if we go back to this chart, we can see that 2 molecules of hydrogen gas plus 1 molecule of oxygen gas gives 2 molecules of water. And if you go backwards, the other way around. So he really came up with this concept and related it to moles. And he said that there was a molar volume. At STP, 22.4 liters of a gas contains 6.02 times 10 to the 23rd molecules, which equals 1 mole. He actually said this part, the 22.4 liters, is 1 mole. He did not know the number of molecules. That was later figured out by other scientists, but because he had led to the development of this idea of the mole, they actually named the number of molecules after him after he was gone. Now, to put this in perspective, that's about 6 gallons. So if you have 6 milk jugs filled with, say, oxygen gas, you have 6.022 times 10 to the 23rd molecules in there. So this really gives you an idea of how small these molecules really are, to be able to have that many of them in 6 gallons, because there's no way we can even conceptualize this number. We talked about that before. We can't even hardly conceptualize a million, let alone 6 with 23 zeros after it. So let's see how we can use this information. I have a question here that says, oh, I gotta find my notes. What volume will 4 moles of ammonia occupy at STP? We know that 1 mole of any gas fills 22.4 liters at STP. So we just do a conversion. We're going to say 4.00 moles of NH3. And we know that 1 mole of NH3 occupies 22.4 liters. We'll have that volume of ammonia. So those cancel. When you multiply 4 times 22.4, you get 89.6 liters of ammonia at STP. 3 significant digits because I have 3 in both of these numbers. We can do more with this. The next question is...
Hey Mom, me and Martha are done.
Okay, shh, I'm recording a video.
Okay, bye.
What volume will 2.5 moles of hydrogen gas occupy at 300 K and 400 torr? Well, before we can know that, we have our 2.5 moles. We need to find the volume at STP. So to do that, we take our 2.5 moles of hydrogen. We say that 1 mole of hydrogen is 22.4 liters of hydrogen, not N, and L. So we multiply 2.5 times 22.4, and we get 56.0 liters of hydrogen at STP. Now we're going to use this number because we don't want to know at STP, we want to know at 300 K and 400 torr. So now we use our combined gas law. So we'll set up our conditions first at STP. And at STP we have V1 is 56 liters. P1 is 760 torr. And T1, remember, is 273 Kelvin. We want to know the volume, so V2, at a pressure of 400 torr and a temperature of 300 Kelvin. So we plug this into our equation. P1 V1 over T1 equals P2 V2 over T2. Plugging our numbers in, 760 torr times 56 liters over 273 Kelvin equals 400 torr times V2 over 300 Kelvin. From here, we want to cross multiply. So $760 torr times 56 liters times 300 Kelvin over 273 cross multiplying equals 273 Kelvin times 400 torr times V2. Okay, I'm going to need another sheet of paper here. So I'll continue this here. Okay, so now we have to divide both sides by these two numbers so that we can get V2 by itself. So we do this. All right, so V2 equals, my units should cancel out to liters for a volume, multiply across the top, divide by the numbers that are on the bottom there, and I get 117 liters. 3 significant digits because I have 3 in each of my numbers up here. Okay, and another type of problem we can do is this, so write that down. A sample of oxygen gas occupies 1 liter when its temperature is 190 K and its pressure is 129 kilopascals. How many moles of oxygen are present? So this is basically like the other problem but backwards. Before we started with moles and we went to volume, now we're starting with volume and moving to moles. So we're going to use the combined gas law to find the standard conditions. So looking at our problem, our initial volume is 1 liter right here. Our initial pressure is 129 kilopascals, and our original temperature is 190 K. We want to find the conditions at STP. So we want to know the volume. We know the pressure at STP is 101.3 kilopascals. Now we have that written in our notes, or I also believe, let me check here, it is also on the very first page of our reference tables here. And the temperature at STP is 273 K, which, if you forget, it's on the first page of your reference tables. So let's plug in our numbers. First, we need our equation, P1V1 over T1 equals P2V2 over T2. Plug our numbers in. So 129 kilopascals times 1 liter over 190 Kelvin equals 101.3 kilopascals times V2 over 273 K. So we cross multiply. 129 kilopascals, 1 liter times 273 K equals 190 Kelvin times 101.3 kilopascals times V2. Now remember, we need this decimal point here so that we know that the 0 is significant. Okay, divide both sides by these two numbers. Cross out my units. I'm left with volume, liters. Okay, so when I multiply these numbers and divide by these numbers here, I get an answer of V2 is 1.83 liters at STP. I'm not done yet because I want to know moles. So now convert to moles. So we start with 1.83 liters of O2. We know that 22.4 liters of O2 is 1 mole of O2. So we have 0.0817 moles of oxygen. 3 significant digits because we have 3 here and here. Okay. So let's take a look at page 268, 1 and 5. I'm just going to do them right here on this video because this is not going very long at all. It's actually a pretty easy day for you. There's no homework after this, so yay! Take a break. Okay, take a look at page 268, 1 and 5, and see if you can answer those, and I will answer those for you here in a couple of seconds. Okay, so number 1 says, why is gas collected over water not pure? Now, at first I thought I was going crazy. I'm like, why did I assign this problem with this section? It should have been with the previous section, but actually the book messed up. They put it in the wrong section, but it's always good to review. So, hey, let's review. The reason is, as the gas bubbles through the water, it combines with water that becomes water vapor. This water vapor contributes its own portion of the pressure to the collected gas. So that's just a review of partial pressures. So let's take a look at 5, which is the new information. How many moles of ammonia produce 134.4 liters of STP? So we have 134.4 liters of ammonia. We know that 22.4 liters of ammonia, or no, yes, 22.4 liters of ammonia is 1 mole of ammonia. So those cancel out, divide here, and when you divide, you get 6.00 moles of ammonia. And that's it for today. You're done. I'll see you later with more.